I know, right? So piecewise functions, they look a little bit different. Don't draw these out quite yet. What I want you to think of is if you look at what the picture I have on the back wall, that is a piecewise function. Real generic, real basic. It's, if you want to think of it, is you're graphing two lines or two functions on one piece of graph paper, and you're just erasing to where the domain is restricted. Okay? So remember, domain stood for what? X values. Range is the Y values, because domain comes before range in the alphabet, same with X and Y in case you've forgotten. But piecewise, bless you, piecewise functions, bless you, are just functions that can be written as multiple parts. Think of it as domain restriction. Okay, they're all defined by the specific domain. And that's where the stuff came into play on Friday, where I had you guys just using the functions and finding what is f of 3. Well, you have to use the f equation, and you see what the domain restriction was, which part of the equation you're going into. Right? If I look at this really generic picture back here, if I look at this one, I would say that this is restricted at -2. And x equals -2 is where it jumps. If it's x is less than or equal to -2, it would be on this graph. If x is greater than -2, it would be on the other graph. That's what it means to be domain restricted. Now, I think there was one question in the on that little worksheet there where it was, the plug and chug stuff, where it said, I think your functions were like 3 or 2, f of x equals 3, or f of x equals 2, I think was one of those. Think of those as just horizontal lines. That's kind of like what that is. So for any value that was greater than -2 on that graph in the back there, it would have been equal to f of x is 6, whatever that range part becomes. Remember, horizontal lines are functions because they pass that vertical line test. Vertical lines aren't functions because they don't. So just like we did, these are like, I think I took these pictures directly from what you guys did in class the other day. So I'm not worried about this. You saw this, we did this, it was easy. You just picked what part you had to go into. And that's what it meant for restriction. Now the goofiness comes into play then when we start to graph these. Now, when we graph these, there's a couple of different ways that I like to show. First of all, on this one, I'm going to change that second one. Instead of being x minus 1, I'm going to change it to x minus 4. That way it's offset a little bit further so you can visualize it a little bit cleaner on the first example. So we'll write this as x minus 4. And when we graph these things, I'm a strong advocate for doing math in pen because it's finite and you're just making sure it's correct. But if you don't want to do math in pen, that's fine. If you have an eraser, it's even better. Oh, we're not out of erasers. Anyway. What's that? Yes, sir. So here's what I would do. When we go to graph these things to start with, don't worry about the domain restriction area. Don't worry about that until you plot your two graphs. The reason that I do that is because I can go back and erase. Right? So I start with my graph of y f of x is x, which is pretty easy. It's just up 1 over 1, up 1 over 1, with y-intercept at 0. Yeah, sorry about that graph paper. It wasn't run off as clean as I hoped. And usually what I do before I start connecting all of my dots, I like to fill up the graph with what it's going to look like. And then I do the other graph, x minus 4, which just means it's the same. They'll be parallel to one another, but it just has a different y-intercept. Bless you. The y-intercept then is that. Once I get that done, then I look at my domain. I look at the first graph. That first graph is only going to be when it is less than or equal to 0, which means at 0 for that graph is going to be a solid or an open circle. Solid. And what direction does it have to go? Left or right? It's going to go left. So basically what I'm doing here is I know for my first graph it's just going to be all of these points go in this direction. And what do I do with the other points? Erase them. Ooh, oh, and I do the same thing with the other graph. And now, again, I go back to the boundary line. The boundary line is something funky going on at 0. I know that this one is greater than 0, so will this 0 be a solid or an open dot? Open. So I already have it as a solid, so what I do is just make it an open dot. Just kind of circle it, and I'm fine with that. Okay. Erase going the other way. And we're going here. And that's what it does when you're doing a piecewise graph. Now, obviously, after you do a few of them, you probably don't need to fill up the entire graph and erase stuff. When you first do some of these, it's pretty helpful to do so because it allows you to visualize it a little bit better. Plus, it forces or reinforces where your domain changes. Okay? Sir?
So, X is less than 0, any less than
Right. Yep. Yep. Yeah, and this is the idea that if you were, go back to what we did on Friday. If I said, hey, what is f of -4? Well, which one of these would you use?
Wait, no.
So at f of x equals -4, my x value would be -4, which means my value of f of x would be -4. So that's just basically telling you where you're going. And that's what you're doing. Instead of it algebraically looking at it graphically. Same idea. Oop, I don't have mine. Someday you'll get good at drawing the brackets as well. It's Jay Leno's face. Big chin.
I gotta go get my car.
Sorry. That is too much money. Seriously. You ever seen garage shows? You know, garage thing, it's just no. For GT, that's what the GT40s, that's what I'm thinking. I'm thinking Ferrari F40. He probably has one of those too. It's a rough one. So just start. You start by plotting, just like you guys have always have. 2x minus 1. And 3x plus 1. So this one, the imaginary boundary of the domain that we're looking around is going to be something funky going on around 1, x equals 1. Now, some people like to do this. Some people will take, when they know that their boundary area is going to be at 1, they'll put a little arrow there, or a little line saying, hey, don't forget, something crazy is going to happen around here. So if I do that, I know that it's sometime when x equals 1, that's where I have to circle a dot or fill in a stronger polka dot and which directions I'm going to be graphing. So the first graph I did was the 2x minus 1, and it says for if x is less than or equal to 1. So that was the graph that I did in black. So will that dot be a solid or an open dot? Solid. And that one is going to go to the left. Oops. Erase my other ones. And then the blue one was when it was greater than 1, and it's going to the right then. I changed that one to an open circle. Now if I move this out of the way, you can kind of see. See how it jumps? It just means it jumps. Okay? It jumps. If you get super fancy crazy later on in life and you do so go into geometry or a math field, you'll have to take axiomatic geometry. Yeah, that's great. It's basically it's called a gap. Bless you. It's called a gap plane. You're right. SFRT. So there, you know how a plane, flat surface, except in all directions. It's what two-dimensional plane that we would look at. We have the spherical plane. You guys know that a sphere is its own plane. Did you know that? Well, there you go. You learned something new today. A sphere is its own plane. Okay. That's called a gap plane. It kind of looks like a piecewise solution. Don't you dare stand up. Just broke you out. You okay? No, I have to get snot rags for my children. So you guys are okay, but I don't. Yes, I give my hand to you. Yeah, right. All right, let's try a different one. Change it up a little bit with the domain. Now the domain is a little weirder now.
So they're all going to be open dots.
All right, so let's see, 2x plus 1 and negative x. This one, you're only looking at the x values going to be between -2 and 6. Do I include either of those numbers? No. So are they open or closed dots on both those spots? They're both open. So I'm looking at between -2 and 6, which would be up here somewhere, so I'll just do that. And I'm looking at this set of values. It's kind of like a segment, if you will. Because it's x value. I just didn't graph it because it still has to go up 2 over 1, up 2 over 1. It'll be up there somewhere. It's not drawn to scale. And I do the other one, negative x. I know that right away, I know that it's looking at the restriction between -8 and -4. So instead of going down and right, I'm just going to go up and left because I had to go that way anyway. And between -8 and -4, I'm looking at this section. And that's what that looks like. No, it really isn't tough because you guys all know how to graph. That's easy. It's just the idea that you can restrict your graphs just by throwing in different domains. Okay? It works out rather clean. Boo! Boo! Questions so far? We all right? It's not bad, right? I was about to say for a Monday, but it's not even Monday. Ooh. They, no, it's good. All right. This is a little bit different. A little, yeah. Yeah, there's 4 of them. But what I want you to think of is they're numbers. Okay? Is there values of x here at all? What kind of lines, don't say straight, what kind of lines are these going to be? Horizontal, very good. They're going to be horizontal. Why are these horizontal lines? Remember that trick that we talked about before? Whenever you have y equals a number, that means the slope is 0 and it's a horizontal line. Well, there is a slope, it's just 0. Now, what this means then, oh, I didn't save any of my old pictures. Oh, no. Oh, that's awful. What am I going to, I don't have all these graphics. Okay. Now, these are what we call a step function. This is called a step function. And I bet you're wondering why they call it a step function. Because it looks like stairs. So my graph is going to be equal to 1 between 0 and 1, including 0, not including 1. So a solid dot, open dot. It goes to 2, solid, open, solid, open, solid, open. It's a step function. It's just walking up the stairs. Okay. These are actually they look really, really weird. They're the easiest ones to do. It's called a step function. No, not that I'm aware of. I don't know if there's an escalator one either. But yeah. A lot of times, there's also a thing called least greatest integer. It's kind of what this means. Between when you are the least greatest integer, you're always. All right, all right. What's the closest integer to that value? 1. Okay.
Okay.
What's the least greatest integer to this? Least 1. One. It's the least greatest. You're always all right. What that means is basically every decimal you're rounding down. That's all it means. Try one more. Did it? Really? Oh yeah, there it is. Yeah, slide.
14.
It's the 14th slide. I didn't know I did that. All right, cool. Whatever. Thank you. So awesome. I gotta figure out how to send myself all my old galleries. Absolutely. I guarantee you're overthinking it, sir. I guarantee you're overthinking it. Seriously. I have no doubt you are overthinking it. All right. So the first step, literally, yeah, it's at 4. So I got to make a horizontal line at 4. On the x value, it starts at 0, including excluding 2. So I know it's going to be y equals 4, so I put it include 0. I start from 0 to 2, and it's an open circle at 2. The reason that it's open is because it's just a less than, and then I just connect them. Correct. And then once it hits 2, it changes its step to include to open. And then once it hits 4, it takes the next step. Think of this as, it's almost like ticket pricing. From a certain amount of time. You guys ever been to Top Golf? Yeah. All right. Top Golf, they have, their pricing is dependent upon the time of day that you get there. If you get there when they first open, it's $25 an hour up until, like, let's say they open at 9. From 9 a.m. to noon, it's $25 an hour. At noon to 4, it's $35 an hour. From 4 to close, it's $45 an hour. So different ranges are different pricing. Okay. Movie matinee. Movies are usually cheaper earlier, and then they get more expensive. It's the same basic idea. Think of this as ticket pricing. That's kind of what this is. Because your ticket pricing, if you go to a concert, the better the seats, the more expensive the ticket. The closer you are for certain sections, the more expensive. The further away you are, the less expensive. Okay. What's that? Oh, geez, I was behind a pillar on Sunday at Wrigley. Oh. You know what? But there was one that came up right. My father-in-law gave my wife and I tickets for the game on Sunday. He said, "Hey, we're sorry we couldn't watch your kids like a week or so ago." I was like, "So I got you Cubs tickets." Okay, cool. Thanks. Appreciate it. It works out really well for us. So we went down there. Yeah, he got us the cheap seats. But no, it was whatever. We still got to go to a game. But yeah, I had a pillar right there, but we were right underneath the press box, and the foul ball came right up, and it just bounced in the stairwell right by us. Yeah. So step functions. They look like they're going to be god awful, but in essence, it's just price increase. Think of that. You're just increasing your price. Just think of the top golf reference. 9 a.m. to noon, it's $25 an hour. Noon to 3, it's 35. It's increasing as it goes along. Does that make more sense? Yes, sir. Yep. Because it looks like they still call it a step function because it just looks like stairs. I don't know. Oh. Trying to think here. What if? Let me see if you can do this. Take a look at this, and I want you to write out the piecewise function for it. This is the last step in doing these things, where you have to be able to figure out what the actual function is by looking at the graph. Now, a lot of times you'll be able to figure out slopes and intercepts without too much of a hassle. We don't try to give you anything too crazy, but I want you to write out the function and then also your domain restriction. Okay? All right? Give that a shot. I don't. We got two equations. You got something funky going around x equaling 1. So the first one I'm looking at looks like I have a slope of -2, -2x plus 2. And the other one looks like I have a slope of 1. And this would be -1, -2, -3. You okay with that?
Yeah.
Okay. Now we have to look at our domain. Remember, something funky happened at 1 when x is at 1. So I'm only looking at the graph of 2x plus 2 when x is less than or equal to 1. For x less than or equal to 1. And for x greater than 1. Okay? That's what we're looking at. Not terrible? Okay. If I'm not mistaken, the sheet that I gave you guys on Friday, I didn't have any of the, I just cut off the top, never mind. I just answered my own question. Sarah, you know me better. All right, so here's what we'll do. I got 4 graphs and 3 write the equations. I got 4 graphs, 3 write the equations. What I will do here in a second is I will attach the PDF file for this to the calendar. Okay? I'll attach the PDF file to this to the calendar here. I think that'll be a lot easier than other stuff. And then that way you guys can just open it up and not have to worry about trying to do all the other crazies. So. If this worked correctly, all you got to do is click here, hit more details. The PDF should be the attachment there. You click on it, it should just open right up for you. There you go. All right? No. If you ever need to check your answers or anything, I have big book answers in the classroom. I'm sorry, what? Probably.